I would like to try answering the questions, where do dictionaries come from? Okay, so when we talked about patch models, when we started, remember it was long ago, we started with a very naive assumption that still gave very powerful priors, that we have some set of exemplar patches, right? And those exemplar patches, presumably they came from representative images. So we did some magic that took patches from those images and extracted from them the set of exemplars. So this magic is typically known in machine learning literature as unsupervised learning, right? So we did some clustering procedure. Clustering is an example of unsupervised learning. And let's try to extend this idea to our more sophisticated models. So let me start with a very simple example of unsupervised learning. Suppose I have a very complicated data space, okay, and I have some distribution of data in this data space. So these are basically, each point is, let's say, a patch. Let's think in terms of patches. So each point here is a patch, and somebody tells me that it's probably not such a bad idea to model our basically this distribution of our patches as some low-dimensional, some k-dimensional subspace in this very high-dimensional embedding space. So basically, not every point in that embedding space is a patch. Okay, so for example, this point is not a patch. It will just look like arbitrary noise. But for example, a point here is something that looks like a patch in a natural image. So if you lump together all the patches that you extract from natural images, you are going to see something like this. And I'm assuming that there is some k-dimensional hyperplane, basically a linear space, that let's assume that it is actually linear and not affine, that we subtracted the origin already. Everything has no DC, so the origin is somewhere here. And the question is, how do I find this linear subspace? Okay. So let's assume that we have examples of patches. I take capital N, and this N is very big. Examples of patches. So I extracted, I harvested zillions of patches from, let's say, from Google image search or from Flickr or from whatever collection of natural images you prefer, and I collect them into something that eventually can be thought of as a matrix F. Okay, so it has many columns. And now I would like to learn a linear subspace model. So what does it mean that I have a linear subspace model? It means that every patch Fi can be represented as a superposition of some basis functions that I don't know, I need to learn them, right? This is the representation of that linear space that I drew before, multiplied by some set of coefficients, some set of coordinates, right? And those coordinates will be k-dimensional because I'm assuming k, low-dimensional space model, right? So I would essentially like to represent my data points, my patches that I collected, as a product of these subspace basis, k basis functions, times data point coordinates, okay? So essentially, if I think of it in terms of matrices, these are columns, phi 1 to phi k, and these are coordinates C1 to Cn. Okay? So basically, for example, when I take the ith patch, here the coordinates Ci, I'm taking with the weight C1, Ci1, the function phi 1 plus Cik phi k. Okay? I'm taking this weighted linear combination with the weights that are determined by the C's of the basis functions phi. Okay? So let me write this simply as a product of phi with C. And this dimensionality reduction problem, this is sometimes called either supervised learning or dimensionality reduction or manifold learning in general, but this is a linear form of manifold learning. Essentially, we would like to approximate f as this product, right? So let's just minimize the difference between f and phi c with respect to phi and c. Okay? And we'll pragmatically select this discrepancy criterion to be the Euclidean norm, because Euclidean norms are easy to optimize. Okay, so this is our problem. Essentially, we are looking for a low rank. What is the rank of this matrix? It has a rank k, or it is actually upper bounded by k. Okay, because the two factors, phi and c, one of them has k columns, another one has k rows. The total rank cannot be higher than k. So we are looking for an L2 optimal rank k approximation of f. So when you hear that you're looking for a low rank approximation optimal in the Euclidean sense, what comes to mind? How do I project my matrix onto a subspace, onto a low rank, basically approximation of the matrix? SVD, right? So I need singular value decomposition. So when I run singular value decomposition, I can represent any matrix F as this product of an orthogonal matrix U, a diagonal matrix sigma, and another orthogonal matrix V transpose of appropriate dimensions, of course. And then I will just take, let's say, usually SVD orders, this sigma will be sigma 1 to sigma n, and sigma 1 will be bigger than sigma 2, and so on. So it's ordered in descending order. So then I take the first k columns of U, I take the first k singular values in this diagonal matrix, and then I take the first k columns of V, or k rows of V transpose. I'm denoting these basically submatrices by UK, sigma k, and VK. And what we get is a rank k matrix that is closest. It's the closest in the L2 sense to the original matrix F. So let's just call these first two matrices phi, and the right matrix, let's call it C. And this is how you obtain this decomposition, which is called typically the principal component analysis, PCA, or the Hotelling transform, or the whitening transform. There are many different names that this very same procedure has. Okay, so this is how we find linear subspace models. Okay, now let's just formalize it a little bit. In PCA, we actually were interested in factorizing a given data matrix. So I'm thinking of F as a data matrix. It contained our data points into two factors. It was a low rank left factor phi and a low rank right factor C, right? So we wanted to do this matrix factorization, and then we use the left factor as the basis, as the dictionary, and the right factor as the coordinates, as the representation coefficients. Okay. Now, if we look through this optic of matrix factorization, what we want to do in sparse synthesis also has this form. The only difference is that the left factor phi is an overcomplete dictionary, and the right factor is a sparse matrix, right? So we have slightly different conditions on these matrices, slightly different constraints that we would like to impose. But the idea is still the same. We want to approximately, well, this never happens exactly for real data, but we want to approximately factorize this matrix into an overcomplete left factor and a sparse right factor. And of course, we can add more priors. We can add group sparsity, we can add non-negativity, and so on and so forth. Okay? So this is basically, from this perspective, sparse synthesis is very similar to PCA. It is just making different assumptions on the factors and consequently ending up with more complicated optimization algorithms. But the idea is exactly the same. Okay? Any questions? So let's see. From this perspective, one of the ways to do dictionary learning goes under the name of method of optimal directions, or MOD. It is not the best or the most efficient way of doing algorithm learning, but I chose to show it to you because it bears a resemblance to PCA. Essentially, we would like to minimize the same problem that we had before, right? This was our PCA problem. The only difference is that the space to which phi belongs is different. It has more columns than rows. It was different. It was the other way around in PCA, okay? And then we would like C also to belong to a different space. And we, instead of constraining C to be sparse, we are just adding a penalty, an L1 penalty that promotes sparse solutions, right? Or we can add L0 penalty here as well. Essentially, what is written here, this matrix norm is just a short hand notation for I going from 1 to n of the L1 norm of Ci. Okay, the columns of matrix C. I mean, since it is basically, since it is homogeneous, right, we can just write it as a single norm of the entire matrix. Okay, now because we have this product here, we have two optimization variables and our objective depends on their product. This usually leads to very non-convex optimization problems. So in the case of PCA, we had a non-convex problem, but this is one of the rare non-convex problems that have a global solution. Eigendecomposition or SVD problems, they are highly non-convex, but we still get, we have an algorithm to find the global solution. If we fixed phi here, we had a convex problem, right? This was our pursuit problem with a fixed dictionary. When we need to find both the representation coefficients and phi, it becomes a highly non-convex problem. And unlike the PCA case, there is no guarantee to converge globally. But what we can do, we can alternate between pursuit steps and dictionary update steps. So we will iterate the following two steps. We will fix phi and solve for C. Okay, and we have seen this problem already. If phi is given, this is just a pursuit problem, right? And then we will fix C that we found and try to update the dictionary. And in this problem, of course, the second term doesn't depend on phi, so we can drop it, and we end up with a quadratic problem. Okay? And we iterate these two steps. You can view it from different perspectives. One of the useful perspectives is to think of this as what is called the EM, or expectation maximization algorithms. Actually, if you think of clustering like k-means also has this structure. It alternates between expectation and maximization steps. So you can also relate this method of optimal directions to vector quantization or to clustering. Okay, so let's quickly look at the second problem that we have, the step in phi. So we want to solve this optimization problem, right? A quadratic objective with respect to phi. And let's simply demand that the gradient of this objective is 0, right? I would like to find a closed form expression for this, obviously. So let's open this L2 norm squared as the inner product of these two expressions. Take the gradient with respect to phi. This is the gradient that we obtain, right? It's just, if you don't remember it by heart, just go to matrix cookbook, and it has all these kinds of gradients of matrix valued functions and of different forms. But this is just the gradient of a quadratic function. Okay, so we demand equality to 0. And from here, we get a closed form solution for phi. It will be given by F times C transpose times the inverse of C transpose. And this is typically, basically, this term here is denoted frequently in the literature by C dagger, and it is called the Moore-Penrose pseudo-inverse. Okay. So essentially, we have this closed form update for the dictionary. Okay? Any questions? So despite the fact that it is a highly non-convex problem, so nothing is guaranteed about convergence. Of course, I'm writing here that I iterate until convergence, but nobody actually guarantees that I will converge to anything and that I will converge to anything useful. Practically, it works very efficiently. It converges just in a few such outer iterations. So I'm calling this an outer iteration because we have an iterative algorithm here that has inner iteration in order to do the pursuit at every step. So we need just 3, 4, 5 outer iterations to converge to a good solution. And it really improves over any fixed dictionary from which you can start. And typically the initialization of this algorithm will just take a certain number of patches from the image and put them as the columns of the matrix phi, and then we'll do these iterations. And it converges very well. In the case of a large K, when we have many columns in the dictionary, the inverse that we have here, which is of the size of K by K, might become very costly. Okay, so if you have, let's say, K 1000, it's still okay. But if it is 10,000, it is already a very costly iteration. And there are better algorithms that scale better with the increase of the dimensionality, and there are also better algorithms that scale better with the increase of the number of data. Here, what is also very costly is this n, the number of columns in F. So instead of looking at all the data, we can do stochastic optimization and look at mini batches, or some basically small samples from our data matrix. So there are also stochastic mini batch extensions for this algorithm that scales better in n. Okay. Again, there is a whole world of dictionary learning that we can talk about, but I would like to show you a different way of thinking of learning that actually leads to state-of-the-art results. Okay. So just to recapitulate, when we had a fixed dictionary, what we did, we solved this pursuit problem with a fixed dictionary, and we obtained essentially a map estimator of the representation coefficients, right? Given an observation y, you estimated the coefficients given the dictionary, and then we estimated the signal, the latent signal, given an observation y with a fixed dictionary. Okay. What we have in dictionary learning is we also minimize over this dictionary. So you can think of what we had previously was conditioned on the dictionary. Now we are also minimizing over this dictionary. You can think of it as an ML estimator of phi, unless you put some prior on phi. Okay. So basically, so this is both ML and map if there is no prior on phi. So essentially, we are doing map estimation of F, now thinking of phi also as a random quantity. Okay, or as a parameter if you work with an ML estimator, but they coincide in this case. Any questions? So I would like to show you, or at least start showing you, a more complicated sparse prior that will lead to a family of estimators that are currently producing state-of-the-art results in not only in image processing, but in practically every field you can imagine. And I'm talking about deep neural networks. So let's see how we get the connection between the sparsity we've seen so far to, for example, to convolutional neural networks. Let's start with our basic sparse synthesis model. We assume that our observation y that we measure on the image was obtained by taking a set of coefficients c and synthesizing with them our latent signal f. So this was our latent signal f, and adding some white Gaussian noise with variance sigma e squared. Okay, and our assumption on C was that it was super Gaussian. right? This is what led to the L1 norm prior in our estimation problem. Okay, and this is just a reminder in case we're dealing with convolutional dictionaries. This is how actually the dictionary acts on the coefficient C. So why do we stop only at one level? Let's assume that the coefficients themselves also admit this model. Okay, so why was, just remember, a slight change of the mathematical objects that we are dealing with. So why again is represented this way? I'm just adding this index 1 to the dictionary and to the coefficients, and the noise sigma will be denoted by sigma 1. Okay, and of course there will be some scale alpha 1 here in the prior of the coefficients that I will eventually, after some simple scaling manipulations, I will translate into lambda 1 in the prior term in my estimator. Okay, but let's now assume that C1 itself is also given by this synthesis model in the dictionary phi2 with the coefficient C2 that also admit a sparse prior. There is some noise maybe of a different variance that is modeled, and of course there might be a different scale here as well. The only thing is that y was a scalar function and C1 is now a vector valued function, right? So this dictionary has to be a dictionary of vector valued atoms, of vector valued functions. Okay? So let's call this a layered sparse synthesis model or a multi-layer sparse prior. Of course, we can continue until, let's say, some L number of levels or layers in this hierarchy. And the map estimator of the latent signal will be simply given by this product of dictionaries multiplied by the last level in the hierarchy of the representation coefficients. Okay? Any questions? So you can think of, so if I'm thinking of the first dictionary as representing a signal using atoms, then the second dictionary already creates molecules out of those atoms, right? So basically it can create more and more complicated structures by going down in the level of the hierarchy. And of course, because we are doing convolutions of functions, even if the support of the functions in phi1 is small, let's say I'm looking at a very small patch, when I convolve many of them, like here, the support that each coefficient at the level L, at the layer L, influence might be huge, might take a significant portion of the entire image. So I'm essentially increasing the scale at which my representation coefficients act. But I'm still assuming very simple and tractable models for every scale, for every layer in this representation. Okay? Any questions? Well, as always, we had this negative log posterior that led to our map estimators, right? So let's just rewrite it. Instead of writing alpha 1, I will be writing this lambda 1, and I will be just keeping the scale of 1/2 in the likelihood term. And then we can do the estimation of the first layer coefficients. It will be just our regular map estimator. I'm taking y as my input, and I'm producing the coefficients at level C1. Okay? Quite simple. This is exactly what we did when we just had one layer of representation. Okay? Let's just add non-negativity. Non-negativity will assume that all the coefficients are non-negative. Again, it will be one-sided exponential distribution in the prior. And I'm adding non-negativity because I would like to obtain something that is used in deep neural networks. I would like a specific type of nonlinearity that is called the rectified linear unit, and it coincides with this non-negative assumption. Okay. Now, how do we actually solve this minimization problem? Well, we can. So remember, we did ISTA, right? It was a particular case of proximal gradient. This is my ISTA iteration. with the specific dictionary substituted into it, right? And let's initialize the first iterate. So this is how the iterate updates C. Let's start with C1 equals 0. So I'm initializing this iteration with 0 set of coefficients. And let's just do a single iteration. So it will not give me exactly this set of coefficients, but it will give me some approximation of that set of coefficients. So this is how my approximated set of coefficients at first level will look like. We'll apply the proximal operator, which I remind you looks like this, right? It's a one-sided soft threshold, which I'm denoting by this S plus, applied to phi 1 adjoint acting on y. And there is some scale that depends on the step size, and the step size also goes into the threshold. So I can simplify this expression. Okay, let's just remind ourselves how the action of the dictionary looks like. This is a synthesis dictionary, right? So this is how it looks like. It's a sum of convolutions. So instead of producing the actual arg minimum, I'm estimating this arg minimum by a single iteration. And the adjoint operator, remember, adjoint operator was the analysis operator. And the analysis operator takes a scalar valued function and it gives me a vector valued function. I'm assuming that I have K1 atoms in my synthesis dictionary. This is K1 in the sum as well. So I'm producing a vector, basically a vector valued function by doing convolutions with these mirrored dictionary atoms, right? This was exactly the technical relation that we have seen half an hour ago. Okay, so also another thing that I can simplify is this scale in the threshold and in the argument. So let's simplify this relation. It will just cancel each other, and I have simply this one-sided soft threshold with the threshold at lambda 1 applied to the adjoint dictionary phi 1 acting on y, the observed input. Okay, and I will write it in this way. Basically, this parenthesis with a plus means that I'm thresholding the values at 0. So basically, anything that is below 0 becomes 0. Okay. And let's write it component-wise. This is the vector of thresholded convolutions of y with these basis functions, with these atoms phi bar, biased by this lambda 1. Okay? Any questions? We can now do the same for the next layer. So in the next layer, I will have C2 estimated from C1. And let's do it just for any k. So in any k, I will have ck minus 1 going as the input, and I'm going to estimate ck. Okay? And again, this will be exactly the same estimator, but I will have the dictionary of the kth layer and some maybe different lambda k appearing in the estimator. Okay. Just one, again, technical detail. Now, you see I'm using a boldface because now this function C is multidimensional. Basically, it's a vector valued function. So the dictionary atoms, this function is basically the values here are in Rk, k minus 1. Okay. This is the dimension of these coefficients because they are used to synthesize in the dictionary of the previous layer and then in the previous layer and then so on until we get to a scalar valued dictionary phi 1, and with that we synthesize the observation y. So so every dictionary atom here is a k minus 1 dimensional function, okay? And basically, I'm doing this by doing this convolution. I'm convolving with these vector valued functions. So basically, the output is also vector valued, and the adjoint. Again, I'm not doing the exact computation. You can do it yourselves. It's exactly repeating what we did with in the scalar valued case. This is how the adjoint going to look like. So these are going to be the elements here, and pay attention that now I have basically these are the output dimensions of phi. So I have k dimensions in the output because these were the dimensions in the input, right? The adjoint changes swaps the domain and the codomain of the operator, and I have this sum. Before we didn't have the sum in the analysis operator, in the adjoint operator, but now I have the sum because the sum goes over the dimensions of the representation vector, and of course over the dimensions of the vector value dictionary functions. Okay, so just again to remember that from the second layer on we have these vector value dictionaries. Okay, and again I will do two things. First of all, I don't have this exact set of coefficients from the previous layer. I will substitute them with my estimate, with my approximation of the estimate of the previous coefficients. And then again, I will not find the exact arg minimum of this minimization problem. I will do just one ist iteration. And this is what I'm going to obtain. Okay? Hi, Mickey, good morning. Okay, so I will finish this slide and then we'll leave the floor to Mickey for his guest lecture. So eventually I end up with this expression for the kth layer, okay? And again, you can write it explicitly as substituting the form of the adjoint operator that we had before. Okay, so I will stop here. I will finish this part next week. We are talking about sparsity, and we are sparse. Probably the weather and the hour. It's something that promotes sparse solutions. So again, I'm applying one ist iteration. This is how my coefficients are going to look like. This is writing the things explicitly. Okay, so this sum pops up because I have again vector valued atoms. Okay, so basically, let's see what we did. We first did this approximate map estimation of the first level coefficients. This is how the estimator looked like. Then we did it for the second layer. Of course, we substituted this estimate here, right? Then we did it for the third layer, and so on. Okay, until we reach the final level L, where we stop. Okay, so just look what happened. We are doing the following operation. We are doing convolution with our input, then subtracting some bias, doing thresholding, and then we apply again the same operation on the result. We again do convolution, subtract some bias, and do this nonlinear operation. We do thresholding, right? So this, it has to be C1. It has to be C1. I apologize for the mistake. And of course, this is C2 as well. And this is CL-1. Sorry, guys. Sorry. It's of course. It has to be basically, it has to be the same vector of coefficients that we are inputting from the previous layer to the next layer. And what we get is a structure that is called in the machine learning literature as CNN, or convolutional neural network. So basically, it looks like this. So I tried to draw it artistically. So we start with our input y. So this is my image y. I apply to it a bank of filters. Basically, these are convolutions, right? So I have let's say in this case I drew three 3 dimensions. So we have 3 atoms in our dictionary. Of course, in practice, we have many more. I'm applying these convolutions. Of course, I need to add a bias term. I'm basically absorbing the bias term into this nonlinearity here. But this is a term that we have to apply. And then we apply this soft thresholding, one-sided soft thresholding that is called ReLU in this jargon of deep learning, of machine learning literature. And we are outputting a vector valued image. So these are channels. Each filter produces a channel in this basically vector valued multidimensional image. Again, in this jargon, this is typically called feature maps or channels in our language of the output image. And basically, this is what the first layer does. Okay, so this is the output of the first layer, and this output of the first layer serves as the input to the second layer. And in the second layer, again, we apply a bank of filters. Now, just pay attention that the filters are basically 3-dimensional filters. Basically, we are also summing along this direction. So in the deep learning literature, this is called tensor convolution, but this is just a sum of convolutions. Okay, basically there is no convolution in this third direction, there is just sum. And there is convolution in the spatial direction along this axis and this axis. Okay, and what we produce again after applying this nonlinearity, this one-sided soft thresholding, we obtain another vector valued image, which is the representation coefficients of the next level in our multi-layered sparse model, and we do it until we reach the final level. Okay. Yeah. So one thing that is phi bar, basically mirrored impulse responses, because we wrote this operator as an adjoint, right? So this was just a conventional representation, but I need to fix this number. So, for example, when I do sparse modeling, I need to fix the size of my dictionary. So this is something that can be done by trial and error. There are ways of learning the dictionary, as we have seen, but again, in learning the dictionary, you need to fix the size of that left factor, which is our dictionary, and the same when we regard this as a convolutional neural network. We need to fix the number of channels, the number of feature maps in the network. So basically, they call it the architecture of the network. So the topology of this graph, if you think of it as a flow graph, has to be fixed. Now, there are methods, some sort of meta-learning methods. You can say, let's search over different architectures in the space of architectures of these networks. So this is also done, actually, very computationally intensive process. It is called NAS or AutoML, neural architecture search or automatic machine learning. It is basically bleeding edge research. It is still not clear how to do it efficiently. But basically, it allows you to also select these kind of meta parameters in an optimal way, if you know how to solve this combinatorial optimization problem. Okay, so let's see. Basically, let's see how we proceed back. So we obtain that set of coefficients. Now let's proceed back. Let's estimate the previous level coefficients from the next level coefficient. So we start with coefficient CL. How do we get the coefficient CL minus 1? So let's just synthesize them with our dictionary. But we also have another prior, that the resulting coefficients have to be non-negative, right? So let's threshold the result. Okay? So this is what we obtain as the result. We are now unrolling back. We want to go back to the input domain. And we do it multiple times, so I'm just writing the expressions explicitly, and until we get to C1, and then we get to F, which is the estimate of the image, which simply synthesizes the image using phi1 with the coefficients C1 and thresholds the results if we assume that the image is non-negative, or we don't threshold the result if we don't assume that the image is non-negative. So what we get is called a transposed CNN, a transposed convolutional neural network. So formally, we are just doing a formal adjoint operator of each layer. Okay, so we just put the nonlinearity aside. We have a convolution a Toplitz's operator, a translation equivariant operator, we are computing its transpose. So what is written here, what is written in this expression before the thresholding is just the adjoint of each convolutional layer. And then we are applying the nonlinearity to impose non-negativity of the coefficients. And very unfortunately, in the literature, this is known as deconvolutional neural network, which is bullshit. It's not deconvolution, because deconvolution, when I'm applying some convolution W, deconvolution means that I need to invert W. This is not an inverse. This is an adjoint. Doesn't invert. W typically is not invertible. So this is not a deconvolutional neural network. It is adjoint or transposed convolutional neural network. This would be the correct term. Okay. So basically, what we get is a structure that is typically called in this literature as a convolutional autoencoder. We have a network that takes our input, our observations y, and encodes them basically using a hierarchy of representation coefficients until we get the last coefficient in the hierarchy. So suppose your convolutional dictionaries have a very small support. So they can encode really small patches, some local information in the image. The deeper we get in this hierarchy, convolution with convolution increases support. So as the result, the last layer coefficients already see many input pixels. So this is in the deep learning literature. This is called the receptive field of the network, like the receptive field of neurons in our visual cortex in the brain. So basically, they see a very big support of an input, potentially really big. Basically, it can be a huge portion of the image. But we are doing it in steps by applying these local, very simple sparse synthesis models. So at least this is one of the ways to see what a deep neural network does. And then we reverse this process and we decode these representation coefficients until we get an image. So basically, by doing this, we are sort of passing our information through a bottleneck here. So there is a bottleneck here. And on the way through this bottleneck, if we have, for example, noise, this noise will be removed if we knew how to build this neural network. So essentially, what we did until now, when we talked about inverse problems, we solved what is called a pursuit problem. It was our map estimation. We solved a minimization process, a minimization problem with some data term. From our probabilistic point of view, this was just a negative log likelihood term, right? And we, of course, augmented it with a prior, this term here, that came from our knowledge of the model of the image. And in the case that we discussed here, it was a sparse synthesis prior. So we are not working directly with estimating f. We are working with the representation coefficients, and then we synthesize in this dictionary phi, and we get the estimated signal f. Okay, so essentially what we had was a map. So this minimizer is a map from the space of measurements to the space of estimated images. Okay, and this can be complicated nonlinear map. Basically, this is an arg minimum of a problem. It can be a crazy map. Okay, and you can think of it as an encoder. Basically, what the minimizer gives you is these estimated coefficients. This is our encoder, and what we have here is a decoder. It's a simple linear decoder. Okay. What a neural network does. So basically, this we did it. Of course we solved it using ist iterations or some other favorite optimization problem. We have basically in the ist iteration we have this linear part that I'm denoting in blue, which comes from the dictionary. It's our linear part, and then we have this nonlinearity that comes from the proximal operator. And in the case of a simple element-wise sparsity, it was just element-wise soft thresholding. Okay. Basically, what this point of view of deep learning proposes you is just to think of the encoder and the decoder as two parametric functions, some complicated nonlinear parametric functions. These parameters alpha and beta, these are all the filter banks that you have in the network, all the bias parameters that you are adding to the output of the convolution before doing the thresholding. Basically, these parameters you can tune them, you can adjust them. The same way we did dictionary learning, you can adjust the parameters directly. So instead of learning a model and then solving an optimization problem to pursue this model, to enforce this model, let's just write the pursuit process as a parametric map from the space of inputs to the space of reconstructed signals and tune the parameters of this map. So it's a different view. You're working directly with the inverse operator. Your inverse operator, this is the solution of your inverse problem. It takes your input y and it produces this output f hat. So let's just write it in a complicated parametric form and estimate directly. So then you can tune the parameters of the encoder and the decoder. And basically, you can learn this network, for example, by demanding that the composition of these two operators is approximately an identity map. So you want, on images coming from your typical distribution of input images, you want this map end-to-end to give you an identity. And of course, when you add noise, this map knows how to essentially project your input signal onto the subspace of signals of interest. So the noise will not be part of the result of this projection. And you learn this. This is called training the neural network by, for example, minimizing this expectation on the space of natural images. And of course, in practice, you cannot compute this expectation. You approximate it by finite sample averaging. Yes.
Why you switched from transposing encoder fees to learning better directly?
So why did I switch from this transposed view? So basically, I have the concatenation of these two operators. Okay, so let me go back. I have the concatenation of these two operators. I can think of this as a parametric map, a nonlinear parametric map. So the parameters, I think I called them, was it alpha or beta? Alpha, I think. So alpha are all the fees. So think of all the fees that I have, phi 1 until phi l. So basically, all these are parameters. It's a finite set of parameters. Plus, I have the lambdas, right? Lambda 1 to lambda k, to lambda l. I can just represent them as a very long vector and learn them, right? By solving a minimization problem. It's an ugly non-convex optimization problem, but one of the magics of deep learning is that it works. And nobody really knows why. Okay? So basically, I'm learning the parameters of this network. Again, instead of learning a model and then solving an optimization problem to pursue it, then it is difficult to learn the model when what I really care about is an arg minimum of that model. But here I just write the inverse operator explicitly as a parametric map. It is a nonlinear parametric map. We have some principled way to understand why we construct it this way, but in this field, practice goes ahead of the theory. These neural networks were constructed just because it worked. And then people are trying to explain it. This is one explanation. There are many different explanations. It's like a magic mirror. You have some tool. You are in love with your sparse models, or you are in love with your random matrices, or whatever it is. And then you see in neural networks exactly the tool that you are used to apply to your signals of interest. And surprisingly, neural networks can be explained from this multitude of views. Okay, and actually, what you will see in the tutorial also, you can parameterize your image in this space of parameters alpha and beta. So basically, when you are solving an inverse problem, you can say, I'm just inputting random noise to my network, and then it does something to this random noise that makes it become an image. So basically, I'm building a generative model. I'm generating an image from random noise. And the parameters alpha and beta tell me basically how random noise is projected onto that subspace of natural images in the very high dimensional embedding space. And basically, I can just solve an inverse problem by estimating alpha directly with a random noise as the input, given some observation y. So basically, it can be done with an untrained neural network, and this is amazing and surprising and not very clear even why this works. So basically, in this structure of repeated convolutions and nonlinear operations, element-wise thresholding, basically we encode some information about how a natural image looks like. So basically, this architecture seems to be essential to getting good results with images, and actually with many other types of signals. So again, as I said, this optimization problem is highly non-convex, and still it works surprisingly well. So it makes me think that basically this kind of dichotomy that we are making, saying that the world is split between convex functions that are solvable and non-convex functions that are non-solvable, this is like a kindergarten type of discussions. Basically, there are many types of non-convex functions. Some of them lead to solvable optimization problems, some do not. So basically, just saying that something is non-convex doesn't mean necessarily that it is not solvable. It just means that we still don't have good enough tools to understand why it is solvable and how. But these are examples why basically that clearly show that some types of very non-convex problems lead to solvable optimization problems, and we still don't have the theory to understand why. And this is something that many people are working on, and there is some progress, but still it is a very active research field. Okay, any questions?